You get it? All right, I will begin. Dear Father, we thank you for this day. Thank you for the students. And I just pray that you'd bless our work today, Lord. In your name I pray. Amen. So this is lecture 24 on ring homomorphism and the field of fractions. So today, among other things, we'll discover that most of the things we said about group homomorphisms have nice analogous results, if you will, in theory of rings. So let's get to it. Definition. What's a ring homomorphism? It's a mapping from, say, let R and S be rings. Then a function, phi, going from R to S, is said to be a ring homomorphism if what? If the following items hold. So number one, it's additive. So phi of A plus B is phi of A plus phi of B. It's multiplicative. So phi of AB is phi of A times phi of B. And then finally, the other structure which must be preserved for a ring homomorphism, because our rings, remember, have identity, we also have to have that phi of the identity in R maps to the multiplicative identity in S. So 1 sub R maps to 1 sub S. Furthermore, if phi is a bijective ring homomorphism, then what? Then phi is an isomorphism of rings. Isomorphism of rings, and we write that R is isomorphic to S. All right? So let me look at an example. So let's look at the mapping phi going from the integers to the integers mod n, right? And I'm going to let the map just be phi of x equal to x of n, right? First of all, is this a function? Certainly z and zn are rings, right? Is this mapping a function? Let me turn the tables here. What if we were to look at beta equal to a beta from zn to z, defined by beta of xn equal to x? Would that be a function? I mean, they look awful similar, but no, the beta is not a function because x is not single valued, right? In fact, there are infinitely many outputs for beta for a given input, right? So beta is far from single valued. But on the other hand, phi is single valued. In fact, that's a function. And you can easily check that it's a ring homomorphism, right? So like phi of A plus B, what would that be? right? And if we look at 1, it maps to 1 sub n, right? And it's also multiplicative. So there you go. This is the so-called natural homomorphism, right? It's also known as the coset map. Why is that? Because if you look at phi here, phi of x is really just equal to nx, isn't it? Nz, rather. I did that wrong. What is it? It's x plus nz, isn't it? All right. Another example is given by phi of z equals to z conjugate. And I think we agreed we're using bars in here, right? I've got a star here. Sorry about that. Stars are bars, yeah. So I'm gonna get rid of the stars here. So complex conjugation, right? Phi of x plus iy equal to x minus iy, right? You can prove that the complex conjugate of a sum is the sum of the complex conjugates, right? And we've talked about this before. You can prove the complex conjugate of a product is the product of the conjugates, right? And certainly, if we map 1, we get 1 conjugate, which is 1 again, right? So you can see that phi is a function from the complexes to the complexes, which serves as a ring homomorphism. In fact, it's its own inverse as well, right? If we calculate phi of z, what do we get? What's the conjugate of the conjugate? Well, you can easily verify that that's just z again, right? So we see that phi squared is just, the identity on the complexes, which of course shows you that phi is what? It's a bijection, right? It's invertible. So in fact, what could we say? We could say more. What kind of, I suppose this is what you would call a ring automorphism, right? It's a homomorphism from C to itself. And what's its order? 2, yeah. Okay. A third example is actually really important and quite abstract. So let R be a ring. And R of x polynomials over the ring, right? Polynomials with R coefficients, as usual. All right. Pick A to be some element of the ring and define phi sub A mapping from the polynomials to the ring by phi A of, let's say, phi A of f of x just be equal to f of A. All right. This is the so-called evaluation map. Now, I can be more explicit here if you'd like. I don't know if it's really needed, but just to be on the safe side, let me be clear about what I mean by this. So we're saying phi A of something like C0 plus C1x plus C2x squared, plus Cnxn is equal to what? You take x and you put A in the place of X, right? That's what I mean by this. So C0 plus C1A plus C2A squared, Cn A to the n. It should be clear that this is an element of the ring because the coefficients C0 through Cn are ring elements, right? And A to any power is a ring element, and the sum of things in the ring is again in the ring. So clearly, if you evaluate a polynomial with coefficients in R, you get an element of R. So this mapping phi sub A from the ring, the polynomials to R is well defined, right? It's single valued because if you plug in A, you don't get two different things, right? Is it a homomorphism? Well, you can check. Easy to check that phi A of f of x plus g of x would be what? That'd be f of A plus g of A, right? Which is phi A of f of x plus phi A of g of x. And likewise, phi A of f of x times g of x is equal to f of A times g of A, which is phi A of f of x times phi A of g of x. So you can see it's additive, it's multiplicative. Does 1 map to 1? What happens when you evaluate the constant polynomial 1 at A? You get 1, right? So there you go. It's a ring homomorphism. The evaluation map is an important example of a ring homomorphism. What more can we say about ring homomorphisms? Well, we can say a lot of things about ring homomorphisms. This is theorem 4.45. And what this is mostly is a collection of things we have seen before, but in the context of a ring now. So here it is. We're going to look at phi, a ring homomorphism from R to S. All right? And we're going to let A be a sub-RNG, not a subring, but a sub-RNG of R. And we're going to let B be an ideal of S. So, and here's our laundry list of things that are true. First of all, for all R in R and n in the natural numbers, we have a couple things. We have that phi of n times R is equal to n times phi of R. So in other words, repeated addition we can pull out. So like phi of 2x is equal to 2 times phi of x, because phi of x plus x is equal to phi of x plus phi of x, which is 2 times phi of x, et cetera, et cetera. And also, more than that though, we also have that phi of r to the n is equal to phi of r to the n. Stupid English. You got to look at the board, right? So, like that. What else do we know? Point number 2, we have that phi A is sub RNG of S. All right, so the image of a subrung is a subrung. Let's see, what else do we know? If A is an ideal, point number 3, if A is an ideal, and phi of R is equal to S, then phi of A is an ideal of S. So what are we saying here? We're saying that if the ring homomorphism is a surjection, all right, then the image of an ideal is an ideal. We had this before for groups. If we had a surjective homomorphism, then the image of a normal subgroup was a normal subgroup for a surjective homomorphism. This was a theorem we proved before. The surjectivity was important. 4, less strings attached to this one, the inverse image of the ideal B is an ideal of R. Again, we had this theorem for groups. We had that the inverse image of a normal subgroup was a normal subgroup. We did not need surjectivity for that. We had this for groups as well. 5, if R is commutative, then guess what? The image of R under phi of R is commutative. Finally, 6, actually it's next to finally. 6, if phi is an isomorphism, if and only if phi is surjective, phi is onto, and the kernel of phi is equal to R and R, such that phi of R is equal to 0, and that is 0. I mean, the first equality there is just the definition of kernel. Sorry. These things. You got it? Uh-oh. There we go. So the first definition, this is just the definition of kernel of a ring homomorphism. All right? It's the additive kernel. Why would we choose the kernel to be the additive kernel? What's the other kind of kernel you might think about here? The multiplicative, right? You could think about all the you can think about all the elements of the ring that map to 1 in the codomain, right? But what makes the kernel, the additive kernel, more interesting for us is that a ring is first an abelian group with respect to addition, right? So half of the proof of all of these things just involves relying on the corresponding results from group theory, because we already know results for the homomorphism of groups, right? For example, we know that if the kernel of a group homomorphism is the identity, that means that the group homomorphism is 1-to-1, right? So this is just a simple way of saying phi, which is, by the way, also a group homomorphism, by just, what makes phi a group homomorphism? Just condition number 1, right? Condition number 1 alone gives you that phi is a homomorphism of the abelian group, which R is, right? R is an abelian group with extra structure. So you can use the fact that a ring homomorphism is a group homomorphism of the underlying abelian group to get that the kernel being 0 implies 1-to-1. Okay? So that's, and actually a lot of the proof of this theorem involves similar thinking. Finally, 7. Phi from R to S is ring isomorphism. Then phi inverse from S to R is a ring homomorphism. Excuse me, isomorphism. So the inverse of an isomorphism is an isomorphism is also true for ring isomorphisms. All right. So I would encourage you to try to prove some of these things for yourself. It's a good exercise for you. We're going to go on. Let's see here. The proofs are, after all, similar to those you've already seen. All right, so theorem 4.46. Let phi from R to S be ring homomorphism then the kernel of phi is an ideal of R. So what did it take for us to show something was an ideal? Do you guys remember? So to show that the kernel of phi, which is what? It's R and R, such that phi of R is equal to 0, we need, what do we need? What was our test for an ideal? What's that? R plus A. I do think we need uber closure, right? We need we need essentially R times the kernel of phi to be a subset of kernel of phi. That's one thing we need. Now, to put that into elements, we need to if let's say X is in kernel of phi and R is in the ring, that should imply that XR is again in the ring, well, in the kernel. And if I haven't assumed that the ring is commutative, I better check what? Rx is also in the kernel, right? I think I need both of those. Yeah.
Originally, I have written down that you need to prove that you show that both AR and RA are elements of A.
Mm-hmm.
That is for A being the subring, or A sub R and G.
Yeah.
But later is that if A is just a subset, you need to prove that the same thing. You also need A minus B is an element of A.
Oh yeah, we're not done yet. This is just part of what we need. We need uber.
So I was wondering if that was it or if that's
Yes. Also, right, and also we need if X and Y are in the kernel. Then what? What you're telling me is I also need to show that implies that Y minus X is in the kernel, right? We need to show closure under subtraction and also products of elements inside the ideal with elements outside in the ring. I think if we can show both of those things and we can show that the set is non-empty, I believe that suffices to show it's an ideal. Right? All right. I hope we're right. So can we do that here? So if, let's let X be in the kernel, then what? Let's let X be in the kernel and R be an element of the ring. Then if we look at phi of XR, or if we look at phi of Rx, what do we get? Right, by the multiplicative property of the ring homomorphism? But what do we know about phi of X? Because X is in the kernel, phi of X is 0. So this is 0, or that's 0. So the product of 0 times anything is 0 again. So therefore XR is in the kernel. Therefore Rx is in the kernel. And that's uber closure. All right? And then the difference is easy. Likewise, if we have x and y in the kernel, then phi of y minus x is equal to phi of y minus phi of x by the theorem that I wrote over there, right? By the exponent laws for ring homomorphisms. We can pull the minus out, right? A special case. Well, okay, fine. Here's my internal logic there if you guys need to see it. Maybe you should see it. Here's the internal logic. Phi of y minus x is equal to what? It's equal to phi of y plus the additive inverse of x, right? Which by additivity is phi of y plus phi of minus x. Then I take n equals to, then by a property of group homomorphisms, which says that the image of the inverse is the inverse of the image, I can pull the minus out. So there you go. That's the internal logic that I used right here. Okay? Anyway, these are both in the kernel, so we're looking at 0 minus 0, which is 0. Therefore, y minus x is in the kernel. And we can conclude that the kernel of phi is an ideal of R. Hey, this is great. Remember what our theorem was for group? What can we say about the kernel of a group homomorphism was what? No one remembers what you can say about the kernel of a group homomorphism? Does not bode well for us. What's that? It is a normal subgroup. So what I'm telling you right now is that the kernel of a ring homomorphism is an ideal. This makes sense because ideals are analogous to normal subgroups. They're the objects which we can form reasonable quotients for, right? There is also a first isomorphism theorem for rings. Say that now. So here's the theorem. 4.47. Here it is. If you have phi, a ring homomorphism of rings R and S, then the mapping from the quotient ring, or factor ring if you like, R mod kernel phi, to the image of R under phi, phi of R, given by R plus the kernel maps to phi of R is a ring isomorphism. In other words, we have that R mod the kernel of phi is ring isomorphic to the image of R under phi. Again, the proof of this is very similar to the one we saw for groups. And I leave it as an exercise for you guys. Next up, we have a theorem which was almost a problem on your last test. Well, the group analog of it was almost a problem on your last test. I had, under the true, false, or possible questions, the following question. Every group can be written as the kernel of a homomorphism and the image of a homomorphism, group homomorphism. True, possible, false. The answer is true, and the reason for that is pretty simple. If you think about any group, look at the identity mapping on the group, then the image under the identity map is the group itself. So it's the image of itself under the identity map, which is a homomorphism. That's kind of cheesy, but there it is. To formulate any group as the kernel of a homomorphism, well, I think that maybe the proper statement is subgroup. Let me write down this theorem. That's the other more interesting half of this problem. Again, phi, a ring homomorphism. Oh, sorry. I was about to give you a rerun. That's no good. 4.48. Every ideal of a ring R is the kernel of a ring homomorphism of R. I think the more interesting statement of the thing I was just saying is that any subgroup of a group can be written as the image or the kernel of a homomorphism of the group. That's probably what I should have said. I think what I said was easier to prove. Any subgroup of a given group can be written as the kernel or the image of a group homomorphism of that group, of the larger group. That's the theorem. That's the true possible false that almost happened to you. All right, now here we go. And in particular, the ideal A is the kernel of the map pi from the ring to R mod A given by pi of x equals to x plus A. I mean, that's the specifics of how it's the kernel of a ring homomorphism. This is the ring homomorphism which you can use. It's just the coset map. Right? So if we look at like pi of x plus y, we've got x plus y plus a, which is x plus a plus y plus a by properties of coset addition, yeah? Which is pi of x plus pi of y. And pi of xy is xy plus a, which again is x plus a times y plus a, which is pi of x times pi of y. So you can see that the coset map, of course, it's additive, it's multiplicative. Does 1 get sent to 1? How does 1 plus a behave? 1 plus a times x plus a, what happens with that? So 1 plus a is the multiplicative identity in the factor ring, which is what we want. We want 1 to be sent to the multiplicative identity again. So this pi, this quotient map, is in fact a ring homomorphism, and its kernel, it's pretty easy to verify, is A itself. And that's the theorem. All right. Let's go on here. Example. Suppose we look at phi mapping from the integers, well, not the integers, polynomials with integer coefficients to the integers. All right? And we're going to look at the mapping phi of f of x. Actually, to be honest, it's phi sub 0. And that is defined to be what? The evaluation map at 0, which is what? What have I done? No? F of 0, right? This is the evaluation homomorphism. So we've already proved that that's a homomorphism. Is it surjective? Yeah, I mean, this is, here we go, phi 0 of z is equal to z for any integer z, right? Definitely surjective. Kind of silly. What's the kernel? What's the kernel of phi naught? So what you're looking at there is f of x in zx, right? Such that f of 0 is equal to 0. What's that mean? Well, that means that we can factor out an x, right? If you have 0 in a polynomial, if 0 is a 0 for the polynomial, the factor theorem says we can factor out x. Right? Search your heart. It's true. And then what is this? This is the principal ideal generated by x. So what does that say about the principal? Well, first of all, it says that that's now we know that that's an ideal from two different perspectives. One, because it's the kernel of a homomorphism. Two, because it's a principal ideal, which is an ideal. But what else can we say? The first isomorphism theorem says what? Z of x mod this is equal to what? Isomorphic to phi of z, which we just said was surjective, so this is isomorphic to z. So what does this tell you about the principal ideal generated by x? Is it prime? Is it maximal? What can you say? If you didn't learn the results from last class, you need to focus and study that again. What we studied last class is important. You need to absorb it into your mathematical consciousness. We need to keep applying those results going forward the rest of the course. You need to know what's prime. You need to know what's maximal. You need to know those two theorems we proved, that when we have what? A ring mod an ideal, and it works out to a integral domain, that's true if and only if the ideal is killing me. Prime. This is evidence that the principal ideal generated by x is a prime ideal. If the quotient is isomorphic to a field, that says that the ideal is maximal. All right. Theorem. R a ring with unity 1, then phi mapping from the integers to the ring by phi of n is equal to n times 1, right? Which, of course, means what? N plus n. Oh, excuse me, it means 1 plus 1 plus 1 plus plus 1 n-fold times, right? That's for n greater than or equal to 1, right? If n is negative, what's it mean? It means repeated subtraction of 1, right? So the proof that that's a ring homomorphism is the laws of exponents for additive groups. I'm not going to prove this is a ring homomorphism. You can prove an exercise, a tedious exercise involving induction will establish this. But it is, in fact, a ring homomorphism. Corollary. is the following. For any positive 4.411, if R is a ring and the characteristic of R equals to n, if the characteristic of R is equal to n, which is greater than 0, then R contains sub ring, which is isomorphic to Zn. On the other hand, if the characteristic of the ring is 0, then it contains a subring which is isomorphic to the integers. All right. What is the proof of that? I best project it. You guys excited about the weekend? Yeah? You guys seem really, really stoked. Is that, I'm allowed to use that word, right? I mean, is that a word that people use? It feels like so 10 years ago, I don't know. Let's see here. So I have posted your, you know, so I posted the solution to test 1, right? Which, you know, I posted both of my solutions to test 1. Very exciting. You can be bemused by their similarity and or difference. Hopefully I don't have any genuine numerical differences. That would mean at least one of them is wrong. Or maybe both. I have found my partial solution to test 2. I'm hoping to have a solution to test 2 posted sometime soon. Let's see here. Oh no, I'm in the future. All right. What? Oh, duh. So sorry. I'll get with it eventually here. I must be saying something very funny today. There's a persistent amount of giggling in here. Let's see here. Is it just the general level of paint fumes in this building? I mean, that's possible. Certainly, this is the season of painting for some reason. Let's see, everyone's stuck inside. Most of the doors and windows are closed. Really not much ventilation. I know, let's paint the whole building. Makes perfect sense. Like, what's the first thing it says on any can of paint you've ever read? What's in, like, bold letters at the top? Use only in well-ventilated areas. Maybe they've got special paint which doesn't need ventilation. I just kind of doubt it. I don't know. Sorry. It's a persistent annoyance of mine. So here we go. This is the one I was just talking about. Again, and what's the characteristic? The characteristic, if it exists and is positive, it means it's a number such that anything you add in the ring that many times, it goes back to 0. So like in Z6, the characteristic is 6, because you take anything in Z6, add it to itself 6 times, 0. Right? Characteristic 0 means it doesn't matter how many times you add the non-zero things to themselves in the ring, they never go back to 0. Real numbers, complex numbers, rational numbers, all characteristic 0. So to prove that there's a subring, you construct this set, which is just multiples of 1. This set is the image of the homomorphism I wrote over here. right? It's the image of the phi homomorphism. And as such, it's a subring, right? Phi of r is equal to s. It's a subring. The kernel of phi, by the way, you can prove is nz in the case of characteristic n. So by the first isomorphism theorem, z mod the kernel is isomorphic to phi of r, which gives you that zn subring in the characteristic n case. And likewise, the kernel of this phi map is just 0 in the case of characteristic 0, which means that z mod the kernel of phi is isomorphic to the image. That gives us the copy of the integers inside a ring of characteristic 0, at least the existence of that. Now, the larger point here is that if we have any field of characteristic p, then f contains a subfield which is isomorphic to zp, all right? And if you have a field of characteristic, then the field contains a subfield isomorphic to the rational numbers. This is proved down here through, I mean, basically, first of all, you've got a subring which is isomorphic to either Zn or the rationals, depending whether you're characteristic, well, Zp, characteristic P, or characteristic 0. And then once you have that, you can use the subring S that I was just talking about to construct the field of fractions like this. You just look at A times B inverse. And the reason that that exists is because you're working inside of, you're starting with a field, right, which means every non-zero thing exists. And so if you take the copy of the integers inside that and then you build fractions from that, you either get a copy of Zp or you get a copy of the rationals up to isomorphism inside your field. So the smallest field, which is contained in all other, the smallest subfield, which is contained in all other possible subfields of a given field, is called the prime subfield. And so you can argue that that prime subfield is either Z mod P or the rationals, depending on what characteristic you're looking at. So this is the so-called prime subfield. So again, we can argue from Steinnitz's theorem that the prime subfield is either the rationals or Z mod P. Now, we take a different turn. We say, okay, if you have an integral domain, D, then there exists a field F that contains a subring isomorphic to D. In other words, I can take an integral domain and I can build a field which takes that given integral domain as a subring. And here's how you do it. You build the so-called field of fractions. So field of fractions, what we do is we look at this set S, which not the same S as I was talking about in the previous page. It's pairs, A comma B, such that A and B is my integral domain and B is non-zero. So A comma B is essentially, we're thinking of that as being A over B, formally speaking, all right? And we're going to say that A and B are, AB is equivalent to CD if and only if AD equals to BC. The way that, where that's coming from is if we have A over B is equal to C over D if and only if what? AD equals to BC, right? So that's where this right here is where the equivalence is motivated from. And then you can prove that this equivalence is in fact a equivalence relation. All right? And once you have that that's an equivalence relation, you can define addition, and you can define multiplication of these equivalence classes. You can prove that the addition and the multiplication of the equivalence classes is independent of the representative, as I do here. And then you can prove that the addition and the multiplication satisfy all the ring axioms. It's commutative, it's associative, it's got the right distributive properties, the whole deal. And after all of that, so what that gives us is that if we look at the set of equivalence classes, we have addition and multiplication well defined. And more than that, continuing on here, you can look at the equivalence class for x non-zero and 0 comma x. We get what? AB plus that gives us that again, which says that this is behaving as the 0 in this set of equivalence classes, right? And if you look at 1 over 1 and multiply, you get AB again for any AB. So you can see that the equivalence class represented by 1 over 1 is serving as the multiplicative identity. Not particularly surprising, right? That 1 over 1 should behave as the identity in this construction. And, you know, I have, here's associativity. You know, you should read through this and think about it through yourself. I might have given you actually a homework problem based on verifying some bit of this here or there. The larger point is that this construction I'm showing you makes sense for any integral domain. What's an integral domain? Commutative ring, no zero divisors, right? So we can build a field of fractions from any integral domain. That's what this construction shows you. Let me make it a little bit more personal. You could take the natural numbers, right? You could join negatives to those. You have the integers. Take the integers, build the field of fractions for the integers. What do you get? You get rational numbers. This is a way of constructing the rational numbers carefully from the integers with abstract algebra. This is how, and this is what, you know, why we would formally say that, you know, 1/2 and 3/6 are the same number. They're two different representatives of the same equivalence class of fractions, right? Or 10/20ths, or, you know, whatever. So this is the definition of the field of quotients. If we have an integral domain D, we can build the field of quotients of D, things of the form A over B like this. And this is just notation for that equivalence class relation I was showing you in the last 2 pages. And we define addition and multiplication in these sort of obvious ways. This reproduces the construction of the natural numbers and so many other things. For example, this is a little bit more out there. Polynomials with integer coefficients form an integral domain. If you look at fractions, f of x over g of x, where these are polynomials with integer coefficients, that gives you a field. All right, the field of fractions, it gives you a field. And the, oh, I've neglected the notation here. How about this one? If we have a, D is polynomials over a field, then we can look at rational functions. That's the field of fractions. The notation for rational functions is f. Look at this. You guys got to pay close attention to this one. Polynomials, rational functions. See the difference? This notation is really compact, but be aware of it. So this is a field that's an integral domain. And likewise, you can do the same thing for, you know, ZP. Then this is the field of rational functions built from polynomials over ZP, which is a field by that construction we just did. Well, I sketched. Honestly, to do all of the gory details of the construction I just showed you, it's like 3 solid pages. There is another more clever way of doing it, which you can read in one of Rotman's modern algebra texts, but I'll shut up as it is now 4 minutes into the weekend and I don't want to take any more of your weekend. Although you might as well stay in here and talk to me about math, because if you look outside, you know, it doesn't look good. You'll be back in an hour? All right, thanks. You can hit it.